Hi class, let's do some linear algebra. Let V be a vector space as usual. Last time, we were starting to explore the relationship between the idea of a basis, the idea of linearly independent vectors, and the idea of a spanning set of a vector space. In particular, we were proving Theorem 24. We proved the first three statements in Theorem 24. Number one, if V1 through Vn spans V, forms a spanning set for a vector space V, then any collection of vectors W1 through Wm, which is a larger collection, m greater than n, this collection is going to be linearly dependent. Statement 2, if we've got some vectors v1 through vn and another collection of vectors w1 through wm, and these form bases for our vector space, then they have to be the same size. And 3, if n is the dimension of the vector space V, as in V has a basis of size n, then any set of n linearly independent vectors will span the vector space V. Okay. Just as a matter of practice, so that we can make sure that we are comfortable with these ideas, let's do a few exercises. Exercise. Say V1 through Vt is a collection of vectors in V. What can we say about the dimension of the span of V1 through Vt? Remember, the spans of vectors form a vector space in and of themselves. So what is the relationship between the dimension of the span of these vectors and, say, the number t? Exercise. Say V1 through Vt are vectors in our vector space, and they're linearly independent. And the dimension of V itself is t. The question is the span of V1 through Vt a proper subspace of V? Last exercise. Let's get a little bit more concrete. Say A is the matrix 1, 2, 3, 4, 5, 6, 0, 0, 1. What is the column space of A as a vector space? All right, let's continue learning or going through the rest of Theorem 24. Theorem 24, number 4. And just to remind you of the setup, V is our vector space. The dimension of V is n. Theorem 24, part 4 says that any vectors v1 through vn such that the span of v1 through vn is our vector space V. Any such set of vectors are linearly independent. As usual, I'm going to walk you through the idea, if not a perfect proof. Just want you to know how this might work. So, if they are linearly dependent, say V1 through Vn span V and are linearly dependent, then without loss of generality, that means that one of the vectors can be expressed in terms of the other vector. So without loss of generality, let's say that Vn is in the span of V1 through Vn minus 1. Okay, so this means that V1 through Vn minus 1 spans V. All right. So if V1 through Vn minus 1 is linearly dependent, we can throw out another vector, and we can continue to throw out vectors until the set that's left is linearly independent. And we know that this process has to end at some point, because if you end up with one vector, of course, it's linearly independent. So what we're going to end up with is V1 through Vm that's linearly independent and spans all of V and is therefore a basis. If M, the size of this basis, is less than n, then this contradicts our assumption that the dimension of V is equal to n, because that just means that all bases have to have the same size, and that size is n. So the final count has to be n. That's the idea. Let's talk about what we can do with this, why we like this, what this allows us to do. Okay, it allows us to check linear independence indirectly. So say we've got 1, 1 and 0, 1 as a set of vectors. We know we can show that this spans all of R2 by looking at a generic element in R2, A, B, and very quickly noting that this is going to be A times the first vector plus B minus A times the second vector. And that means that 1, 1 and 0, 1 spans R2. Since there are two of them, and the dimension of R2 is 2, by 4, 1, 1 and 0, 1 are linearly independent. For small vectors like this, perhaps this is not the most efficient way to check linear independence, but you can imagine as the vectors get larger and as the size of the sets get larger, this might be a good thing to have in your back pocket as a tool. Let's move on to Theorem 24, Part 5. Here's what it says. No set of fewer than n vectors can span V. Here's the idea. Say the span of W1 through Wm is V. And remember, V is also the span of B1 through Bn. Let's say that this is a basis for V. Let's say that M is strictly less than N. Then, by 1, B1 through Bn will be linearly dependent. That's a contradiction because bases are formed by linearly independent vectors. Okay, why do we like this? What this allows us to do Say A is some matrix. One, two, three, four, five, six. Say we're looking at the equation AX is equal to B. We'll know that it's not guaranteed to have a solution because two vectors don't span R3. So there exists a B that's not in the column space of A. And so if you pick such a B, then this equation will not have a solution. So Theorem 24 part 5 allows us to quickly analyze whether we think a system of equations will have a solution or not. Let's do part 6. Theorem 24 part 6. Any set of linearly independent vectors is either a basis or can be expanded to a basis. All right, here's the idea, why this might be true. Say we're looking at the span of V1 through Vk, where k is less than n, and n is the dimension of V. Then this span is a proper subspace of V. Say these V1s through Vks, say these are linearly independent. Well, by 5, this means that there exists a Vk plus 1 not in the span. Simply because it's a proper subspace, right? And then we will also know that V1 through Vk, because V1 through Vk is already linearly independent, and Vk plus 1 is not in the span of V1 through Vk, then V1 through Vk plus 1 is linearly independent as well. We're going to keep adding vectors until there are n linearly independent vectors. Then by 6, by 3, these also span V. Then V1 through Vk, Vk plus 1, all the way up to Vn, will be a basis. That's the idea. Why do we like this? What does this allow us to do? Well, what this allows us to do. All right, so we got 1, 2, 3, and we've got 4, 5, 6. And we know that they don't form, say we know that they don't form, well, we know that they don't form a basis for R3, because we need at least 3 vectors to do that, but we know that they are linearly independent. This means that there exists an ABC, some other vector in R3, such that 1, 2, 3, 4, 5, 6, ABC is a basis for R3. We can expand our original list to a basis. For example, ABC could be 0, 0, 1. That'll work. All right, now for the final part of the theorem. Theorem 24, part 7. Any spanning set is either a basis or can be pared down to a basis. In other words, any spanning set contains a basis somewhere in there. Here's the idea for why this might be true. Say V1 through Vk is a spanning set for a vector space V, with k strictly greater than n, when remember, n is the dimension of V. Then, by 1, they are linearly dependent. Without loss of generality, let's just say one of them can be expressed in terms of the other. So let's say Vk is equal to C1 V1 plus dot 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 plus Ck plus 1, Ck minus 1 Vk minus 1, where the Ci's are real numbers. We're going to remove Vk. We're going to continue to remove vectors in this way. Until the set is size n. Then, what do we have left? Then, by the fact that it is a spanning set, of the right size, by 4, they are linearly independent, and therefore form a basis. That's the idea. All right. What can we do with this? Say we've got 3 vectors, 1, 2, 3, 4, 5, 6. And say they span R3. They span R2. We know we can remove a vector to get a basis. For example, 3, 4, 5, 6 forms a basis for R2. So ends Theorem 24, all 7 parts of it, and our justifications for why each one of those 7 parts is useful to us. Of course, you should have lots and lots of questions. There's one that I want to draw your attention to. Say V is a vector space, and we now know that it can have multiple bases. Is there a reason? Is there ever a reason we would want to use a different basis? Think on this. Talk to you next time.